A geometric sequence is one in which each consecutive term in the sequence is gained by multiplying the previous term by some number, called the common ratio. The formula we use for finding the nth term of a geometric sequence, a sub n, as it was with your arithmetic sequence, is the nth term. A sub 1 is your first term. But now we have something called r. R is the common ratio. That's the number you're multiplying each consecutive term by. And the common ratio is really easy to find. You just divide the second term by the first term in the sequence. And n is your term. And notice in the exponent is an n minus 1. So let's do an example. Find the first 4 terms in a geometric sequence and the nth term if a sub 1 is 3 and r is 2. So if the first term is 3, to get the next term you multiply by 2, so you get 6. And then you multiply by 2 to get 12. And then you multiply by 2 to get 24. The nth term is going to be a sub n is equal to 3 times 2 raised to the n minus 1. So now we could use this formula to find any term down the road. Let's find an equation for the nth term of the geometric sequence 2, negative 10, 50, negative 250, 1250. So to write the nth term, you need to know 2 things. You need to know the first term and you need to know the common ratio. Well, I already know what the first term is. The common ratio you can find simply by doing the second term divided by the first term, which is negative 5. So the nth term is just 2 times negative 5 raised to the n minus 1 power. Let's find the 8th term in the geometric sequence 5, negative 15, 45. In order to find the 8th term, first I need to know the first term and the common ratio. Well, here's the first term. The common ratio is the second term divided by the first term. So to find the 8th term, it's the first term times the common ratio raised to the n minus 1. Now the way that I would put this in my calculator is I would evaluate the 8 minus 1 first and do 3 to the 7th power. Then I would multiply it by 5. And you're going to find out that the answer is 10,935. The third term of a geometric sequence is 63 over 4, and the 6th term is 1,701 over 32. Find the 5th term. Well, I can start this problem by basically setting up a system of 2 equations, 2 unknowns. So the first equation is 63 over 4 is equal to a sub 1 times r to the 3 minus 1. And the second equation is going to be 1701 over 32 is equal to a sub 1 times r to the 6 minus 1. Well, what I'm going to do is I'm going to flip-flop these, and I'm going to put a sub 1 r to the 5th over a sub 1 r to the 3rd. I'm going to make that equal to the one with r to the 5th in the numerator goes with the 1701 over 32, and the one with r to the 3rd, which is in the bottom, goes with the 63 over 4. Now what's going to happen in this problem is that the a sub 1's are going to cancel, and you're going to be left with r squared is equal to, hold on, sorry about that, let's try that again. 3 minus 1 is 2 last time I checked. Alright, so let's go back to this. So r to the 5th over r to the 2nd is r to the 3rd, and that's going to equal what you get when you divide 1701 over 32 by 63 over 4, and you're going to get 27 over 8. To solve for r, you must take the cube root of both sides, and you're going to find out that r is 3 over 2. Well, now I know what the common ratio is. Now I need to go back and find the first term. So I'm going to plug this r back into either of the original 2 equations. I'll pick this one. So a sub 1 times 3 halves to the 2nd power is going to equal 63 over 4. Well, 3 halves squared is 9 fourths. And then when I divide the other side by 9/4, I'm going to find out that a sub 1 is 7. So now I know the first term and the common ratio. Now I can go and find out what the fifth term is. The fifth term is the first term times the common ratio raised to the 5 minus 1 power. So when I plug that in my calculator, I'll get a decimal, hit math, enter, enter, and I'll find out it's 567/16. We had to do a lot of work to get to this answer, but we did get to this answer. We can also find partial sums of geometric sequences. That means when we want to add a certain number of terms in a geometric sequence. The formula that's in your book is a little bit different than the one I wrote here. There are a couple of ways of writing this formula, and this one I have found works the best for students. S sub n is equal to a sub 1, r to the n minus 1 over r minus 1. So let's try this formula out and find the first five, or the sum of the first 5 terms of the geometric sequence 1, 0.7, 0.49, 0.343, dot, dot, dot. In order to find the sum, you need to know the first term, and I do. You need to know the common ratio, which is the second term divided by the first term. And you need to know how many terms you're adding. So the sum of the first 5 terms is the first term times the common ratio to the nth power minus 1 over the common ratio minus 1. Now the way that I would do this in my calculator is I would first evaluate what's between the parentheses. So do your numerator, divide it by your denominator, and then since a is 1 on the outside, when you multiply by 1, doesn't really change the answer. And you should get 2.7731. This particular sum is a special geometric sequence. So in order to find the sum of the first I guess it's the first 5 terms, because we're going from k is 1 to k is 5. You could find each term by plugging in each number and then add them together. Or you could start by finding the first term, which is just negative 14/3. And the common ratio is just the value in the parentheses. So if we want to find the sum of these terms, there are 5 terms. Terms 1, 2, 3, 4, and 5. So the sum of the first 5 terms is the first term times the common ratio raised to the nth power minus 1 over the common ratio minus 1. And again, in order to do this in my calculator, I would evaluate this, I would divide it by this, then I would multiply it by the negative 14/3. Hit math, enter, enter. You'll find out it's negative 770/243. There's a certain type of infinite geometric series that has a sum. There are 2 things that can happen when you have a sequence of numbers. The sequence of numbers can continuously get larger and larger and go to like positive infinity, or they could get smaller and smaller and go to negative infinity. We say that those types of sequences diverge. But sometimes the numbers in a sequence continuously get smaller and smaller, or closer and closer to some value. In Algebra 2, we call that a horizontal asymptote. So when a sequence converges, it's going to have a sum, even though it's infinite. And the formula for the sum is a sub 1 over 1 minus r. You're going to know if a sequence converges or diverges by looking at the common ratio. If the common ratio is less than 1, it's going to converge and have a sum. If the common ratio is bigger than or equal to 1, it's going to diverge and therefore has no sum. Arithmetic sequences do not have a sum when they are infinite. Hence the reason for arithmetic sequences, we can only add a finite number. Let's look at these two series and determine whether each infinite geometric series is convergent or divergent. If it's convergent, we can find its sum. So the first series, the first term is 2, and the common ratio is the second term divided by the first term. Well, 2/5 divided by 2 is 1/5. So since that value is less than 1, it is convergent. And since it's convergent, it has a sum, and its sum is the first term divided by 1 minus the common ratio. Now I would do the 1 minus 1/5 first. You're going to get 4/5, and then do 2 divided by 4/5, which is going to give you 5/2, which is its sum. Oops, I didn't write a 2, did I? Said 5/2, I didn't write it. Okay, for the second one, 1 plus 7/5 plus 7/5 squared plus 7/5 is the third. Here's the first term. And the common ratio is the second term divided by the first term. Well, 7/5 divided by 1 is 7/5. But 7/5 is bigger than 1. If it's bigger than 1, then the series is divergent and therefore has no infinite sum. The neat thing about infinite geometric series is they can be used to find the exact fraction that represents some sort of repeating decimal. Now, in this repeating decimal, the 2.351, notice that the line is over the 3, the 5, and the 1. I'm trying to make it look more like that. It's still not working. Let's see. There we go. Try that. There we go. That looks better. So the 351 is the part that, oh, no, I shouldn't say the 351. Let me go back. Sorry. The example that I'm looking at actually only has us over the 5 and the 1. Sorry about that. What the line over the 5 and the 1 says is that the 5 and the 1 repeat. So the first term in this sequence is going to be (23/10). The 10 comes from the fact that the 3 is in the 10th place. The next term is going to deal with the 51. And I want you to remember place value here for a second. This was the 10th place, the 100th place, and the 1000th place. Since the 1 is in the 1000th place, we're going to put the 51 over 1000. So now the next part where it repeats, thousandths, 10,000ths, 100,000ths. And so on and so forth. And this ends up being a repeating decimal. So the first term, we're not going to worry about this part right now. That'll come back in a few minutes. The first term of the part that's actually in the infinite geometric series is the 51/1000. The common ratio is what you get when you divide the first term by, or the second term by the first term. Well, the 51s end up going away, and you end up with 1,000 over 100,000, which reduces to 1 over 100. So the common ratio is 1 over 100. Well, now that we have the first term in the common ratio, we can do S is equal to 51 over 1,000, that's the first term, over 1 minus the common ratio. And you end up getting 51 over 990. Well, now we have to deal with the 23/10. If you add those fractions and reduce it in your calculator, you're going to find out that the fraction whose repeating decimal is 2.351 repeating is 388 over 160. However, there's a much simpler way of doing this using the graphing calculator. If in the graphing calculator you type in 2.3 and then you start 51, 51, 51, 51, 51 until you fill up at least one whole line in the calculator, then you go use math enter, it will turn it back into the exact fraction for you. It's kind of a neat little trick on the graphing calculator for changing repeating decimals back into fractions. But remember, in order to use math enter to change it back into a fraction, you have to keep typing in the repeating part so that it fills up at least one line on the graphing calculator.